Good morning and welcome to today's webinar. My name is Beth Capellas and I'm the Sales and Support Manager here at Triangle MicroWorks. Thanks for taking the time out and joining us today. Triangle is hosting a free multi-part training series called IEC 61850 Hands-On Training. Today we're presenting part 2, Digging Deeper, Data Modeling in SCL. Future training modules will cover topics such as bottom-up versus top-down, IEC 61850 engineering process, communications in 61850 MMS client and server, goose and sample values, testing, commissioning, and virtual isolation, and several more. Each training will be followed up with a companion lab exercise to help reinforce the key concepts that we introduce in each of the training sessions. We will also provide extended trial licenses to the tools that you see in the training to complete the lab exercise. Once you complete, you can submit the exercise to Triangle for review and are eligible to receive a certificate of completion. If you'd like to receive notifications of these future training and lab exercises, please answer the survey at the end to receive the notifications. I should also mention part 1 was called Foundations of IEC 61850, from Legacy System to Digital Substations. That was held about 6 weeks ago. If you missed it, no worries. You can find the recording on our website. I will also drop a link to that in the chat. And you can find the companion lab exercise and reference document under handouts in the webinar toolbar, as you see in this picture here. So with that, I'd like to go over some housekeeping items before we kick off the training. So the training is scheduled to be 90 minutes long. The audience is on mute, so please submit your questions online using the webinar toolbar under the section titled Questions. You can submit questions as soon as you have them. Please don't wait until the end. We will begin answering questions online as we have several engineers monitoring the questions and responding to them directly. We have a lot of material to cover today, so we will most likely save questions for the end. We might try to take a break if we do have extra time in the middle. But we'll take some of the questions that are coming in and try to answer them live if we can. But at the end of the day, again, don't wait to the end. Once you submit them, we will be responding to them as quick as possible. So with that, I'd like to introduce the folks behind the scenes that are answering the questions. Today we have with us Jim Coates, President of Triangle MicroWorks, Sri Engula, Senior Developer for TestSuite Pro, one of the tools that you'll be seeing here today, and Eric February, Senior QA Tester. Next, I'd like to introduce our speakers. First, we have Christoph Brunner, President of IT for Power. Christoph is a well-known utility industry professional and 61850 expert with over 40 years of industry experience. Christoph has been involved in the development of the standard since the beginning. He's the convener of Working Group 10 and member of Working Group 17, 18, and 19 of IEC TC 57. He is an IEEE fellow and a member of several IEEE working groups, as well as a member of the PSRC main committee and the subcommittee H. Next, we have Jackson Moore, application engineer at Triangle MicroWorks. Jackson received Bachelor's of Science degrees in both electrical engineering and computer engineering from North Carolina State University and has a background in power system engineering. Prior to joining Triangle, Jackson spent over 5 years as a microgrid system engineer, where he designed and developed load management control systems for multi-source microgrids. Currently, Jackson works with our customers and development team to understand and solve the challenges our clients face. So now that you know everyone, I'd like to give you a little bit of background on Triangle MicroWorks. We were established in 1994 and have over 30 years of communication protocol experience. We are headquartered in Raleigh, North Carolina, and have customers in over 70 countries. We work mostly with equipment manufacturers, electric utilities, and system integrators. The products we offer all support the standard SCADA protocols and fall into 3 categories. First category is source code libraries. We license source code directly to manufacturers for use in their devices and systems. This allows for a much faster time to market and greatly reduces their cost in development time. Licensing a source code library also includes support for your implementation and any issues that may arise in the field. We also provide testing tools supporting the libraries and the protocols. These tools are used for communication testing in the lab or field. They are designed to troubleshoot, simulate, and automate testing for both a single device or a complete substation. Lastly, we also provide a SCADA data gateway supported on both Linux and Windows for protocol translation and data concentration with standard SCADA protocols as well as OPC. It is available as software only or pre-installed on hardware. We are heavily involved in the standards committees that support SCADA protocols like UCA Group for 62850 and DMP user and technical committees. Through our participation, we help define the protocols, stay up to date on the changes taking place, and ultimately provide feedback based on our customers' needs as the protocols continue to evolve. So now that you know a little bit more about Triangle, I'd like to go ahead and hand it over to Christoph to kick off the training.
Thank you, Beth, and good morning, everybody, from my side. Before we go into the details of the data model, I will repeat a little bit of the basics that you have learned in the first webinar part from Jackson that he gave a while ago. As you learned, IEC 61850 is not only about communication. IEC 61850 has basically 4 different key parts that we address. We address the communication, yes, but we also address the semantic models, we address engineering, and we address testing. A quick overview on some of the key elements of IEC 61850. We typically have our devices that we call ID or intelligent electronic device. In a system, an ID has a data model, has information that it provides depending on its functionality. The information that is available based on the standard is defined in the parts 7.4 and 7.3. We also discuss how we exchange information. So the way how information is exchanged, we find in the part 7.2. Today, as mentioned, the focus will be on the part 7.4 and 7.3, where we basically define the data model. As a quick reminder, so the data model in IEC 61850, the data model of an ID basically contains all the information that is required by functions supported by the ID. As you have learned already in the first part of the webinar, that information in 61850 is typically grouped based on the functional elements that we have in the device. And such a group is called logical node in the IEC 61850 standard. Before we go deeper in the details, we will show you again how that looks. And for that, we will use the substation demo that we already have used in our first webinar and that we are also using in the trainings that you can do. What we see here on this slide is a reminder on how this substation demo looks. We have basically 4 bays, a single bus bar substation with 2 line bays, 2 transformer bays, and then we also have a measurement bay for measuring the bus voltage. The functionality in this demo, we have for the control and measurement, we have control of circuit breakers and switches. We calculate RMS values for current and voltage. Then for the line base, we have various protection aspects. We have a distance protection with 2 zones that we model. We have a line differential protection, breaker failure function, reclosing, and synchro check function. For the transformer base and the bus bar protection, we use differential protection. Now, how does this look in IEC 61850? As we just mentioned, basically in IEC 61850, we group the information according to the functional elements, and that results in the logical nodes. And the list on this slide shows you the various logical nodes that are there to address the functionality that we model in this substation demo. And Jackson will show you that in the demo again. So basically, we have in our demo for each of the bay 4 IDs. We have a couple of IDs on station level. Then we have for each of the bay 4 IDs, and we will focus in the demo on line 1, where we have a bay controller, we have the line protection unit, we have this interface to the switch gear, and we have the merging unit. And after that, with this quick introduction, I hand over to Jackson for the first demo to refresh a little bit these basic aspects.
Thank you, Christoph. All right, yeah, in just a moment, I'll be sharing my screen and I'll be showing you guys some of this in action using some of our tools.
Okay, you should have the
So,
screen.
perfect. What you see up on my screen now is Test Suite Pro. If you guys have used Test Suite Pro in the past, this might look a little unfamiliar to you. Maybe you saw it on one of our past webinars, or you completed the lab exercise that went along with webinar 1. So what you see here is actually Test Suite Pro version 5. So this is a yet unreleased beta, but it does have all the features that you've known and love in Test Suite Pro version 4.7, which is currently released. We do have some new features and functionalities as well, which I'll be talking about later on in a future webinar. But for now, it's a lot of the same features and functionality, just a different look and feel. We've brought the user interface to be more in line with some of our other tools, most notably DTM or Distributed Test Manager. So a little bit about what we're looking at. Over here on the left-hand side, you'll see a collection of IEDs. So as Christoph will be telling us more about later, these are defined in an SCD file, or System Configuration Description. And based on their prefixes, you can kind of get an idea of where they are and what they do. So for example, they all start with D1. They're all in the same voltage level, which has been titled D1 in SCL. And then if we look at our line 1 IEDs, we can see that I have 3 listed here. So the BCU, or Bay Control Unit, up at the top, the LPU, or Line Protection Unit, below it, and then finally the SCU, or Switchgear Control Unit. As the names imply, the Bay Control Unit is going to be doing Bay level control. A Line Protection Unit, this is where we'll see all our protection functionality. And then finally, the Switchgear Control Unit will interface with the actual conducting equipment, the breakers and switches. So if we want to browse the model of one of these, which is what I'm doing here in the middle pane, using the model browser, I'm looking at it using the kind of typical 61850 hierarchical view. So if I expand out the data model for this particular IED, my Bay Control Unit, I see that it has 2 different logical devices, measurement and control. If you remember from last time, great. If not, don't worry, Christoph will be covering it in more detail. Logical devices are just a way for us to break up the functionality of our device into different containers. So here, measurement, most importantly, it's going to have our MMXU, which will be how we're reporting measured values up to a SCADA system or gateway, and then our control logical device down below. So here we have the different control functionalities like our CSWIs. This is the control switch that a SCADA operator would ultimately interface with in order to operate a breaker or switch. And then we also have our supervisory interlocking performed up here at the Bay level. If I navigate over to, let's see, one of my other IEDs, for example, the Line Protection Unit, I'll see that this particular IED also has 2 logical devices, control functionality, and we'll be talking about the recloser example a little bit more here in a bit, but that would be contained in control. It's not supervisory control or Bay level control like we saw in the Bay Control Unit, but control related to protection. Down in the protection logical device, this is where we see the different protective elements. So the PDIF logical node, again, all of these are different logical nodes modeling a specific function or piece of conducting equipment. RBRF for breaker failure down here in the line. Finally, switching over to the Switchgear Control Unit. This is the last IED in this particular bay. Here is where we're actually going to interface with the specific conducting equipment. So this IED only has a single logical device, and the logical nodes that I want to draw your attention to are down here at the bottom. So 61850 gives us the ability to have hierarchy and semantics. When we talk about hierarchy, of course, we're talking about the IED, logical device, logical node, data object, data attribute, those containers within containers. When we're talking about semantics, I mean the ability to describe our data in our model in a way that we can understand. So in this context, QA1 references a particular breaker by name that we will have in our substation. And then XCBR is our interface to a specific circuit breaker. And then this 1 at the end is just an instance number. You can see 1 and 2 down here for XSWI. These are going to be interfaces to do 2 different switches also in this bay. And they will have the names QB1 and QC1. So for right now, I'm not going to open up these logical nodes and take a peek inside the data objects and data attributes. Instead, I'm going to go ahead and turn it back over to Christoph, and he'll provide a little more context, and then we'll come back over here into Test Suite Pro in a few minutes and dive a little bit deeper.
Okay, thank you, Jackson, for that quick refresh. And so let's now get started into the more details. So in my presentation, I will first discuss a little bit the elements of the data model, summarize again what are the different elements, then dig a little bit deeper into the data model. I will explain you how the data model is standardized in the different documents, and at the end we will also briefly start discussing a little bit some aspects of the system configuration language that we will explore further in more details also in one of the later webinars. Coming to the elements of the data model, we already learned in the part 1 and in this little refresh that typically our data model consists of logical devices, logical nodes, data objects, and data attributes. But when we are discussing data models, we also need to discuss about the data structures behind that are defined in what we call common data class and constructed attribute class. A refresh on the data model, as Jackson has mentioned, the data model is hierarchically, as you have seen. We have the IDs. Within the IDs, you have seen logical devices, logical nodes, data objects, and data attributes. At the example that Jackson has just shown, we have the switch control unit, the SCU. We have then control, the logic device that we have seen in that, which was the control. We have the breaker interface, which was the logic node XCBR that Jackson has shown. We have the position, and in the position we have a data attribute STVal, which really carries the value. So while a lot of these elements are the structure of our data model, somewhere we have our leaf logical nodes. That's where we really find the values. So in this case, STVal will hold the position and will indicate if the breaker is open or closed. What we see down here, that's the hierarchical path. So the reference to the data objects or to the attributes is using the hierarchy of the model to have a unique identifier of the object that we want to refer to. Okay, so this slide shows an example of a logical node. As we have mentioned, the logical node is basically a container for functional related data. And the logical node has a collection of data objects, like we see here, the blue part, that's really the data object specific to this logical node. In this case, it's the interface to a switch, like a disconnecting switch or an earthing switch. We have typically the data attribute that holds the position, but we also have additional data attributes like block opening, block closing, and whatever. The gray part that we see here, this is a set of data objects that we have in all the logical nodes that we mainly use for the management, like we have nameplate information. We will discuss that, some of the usage of these elements in future webinars. When a logical node is defined, we have the indication of the data objects. We also have indications if this data object is mandatory or if it's optional. And we have a reference to the type that makes out this data object. And that's what we call the common data class. In this case, double point control, that will be the common data class where the position is made out of. So that's a structured type for this data object. To give you some ideas of the logical nodes, the IEC 61850 part 7.4, which is defining these logical nodes, is grouping them. And the first character of the logical node identifier of the 4 characters gives us an idea of the group. So we have, as examples, we have logical nodes that are protection related logical nodes. We have an example here, the differential element. We have protection related logical nodes. That's typically logical nodes that become relevant when a protection trip happened, like the breaker failure. We have interface logical nodes, like the circuit breaker interface, control, switch controller, measurement, a measurement unit, or also power transformer. The numbers here indicate the number of logical nodes in this group as they were in edition 1. In the meantime, the standard has progressed, so we have also a little bit more logical nodes in these different groups. Now let's have a look at the common data class. As I mentioned before, common data classes are basically structured types that define what attributes are in the data object. If we take again the example of the position of a circuit breaker, the common data class that we have here is what we call DPC or double point control. So basically we can say that a common data class is a reusable predefined set of data attributes. Yeah. Again, we have first a group of data attributes that relate to the real values, the values that we have in our system, like the status value for a double point control. We have quality, timestamp. So basically in IEC 61850, when we have controllable data points, we combine the status value that we can read back from the object as well as the control point into the same common data class. That's why we have these controllable common data classes. We also have attributes that are more related to that are more like metadata. So we have configuration attributes. As an example, if our control model here behind supported is a select before operate that we can configure in the configuration parameter control model. Then we have parameters like a select before operate timeout. That's the time between the select and the operate that you have as a maximum that you have to bring the operate. So we can also configure these parameters as part of the data model. And depending on the common data class, there is various configuration attributes associated. Last but not least, we have data objects related to substitution, to blocking, information transfer. We will not discuss those in further detail today. Another element that we have, as we have seen, we grouped these attributes depending on their characteristics, on their functionality, and to group them, we have what we call a function constraint. So this first group, that's where we really find our live information. These are the status attributes, and they have a function constraint ST. We have as an example here the configuration attributes or description attributes, and also they have their specific function constraint. So a function constraint is used to indicate the group that the data attribute belongs to, but we also define based on the function constraint what services can be applied. As an example, of course, if you have a configuration attribute, we can write information on them. So we can have the services to write information used. On the status attribute, we can only read them or report them, but we cannot really write the status attribute because that's the value captured from the network. This slide again shows a few examples of common data classes that are also grouped. We have single point status is one example for status information. We will talk about the protection related data attributes, common data class a little bit later. We have common data class for analog values, measured values. We also have common data classes for the power system when we have the three-phase values that we typically have in our power systems. We have controllable objects, and we also have settings. So we also have in our data model data objects that are settings of the protection functions as an example, and we also have nameplate information. The data attributes, they can have further structures beyond. So in the simplest case, a data attribute is just of a basic type, like the status value that we have seen before, which is a double point status. But in some cases, we have further structures beyond, and that's when we talk about constructed attribute classes. We have an example here, a constructed attribute class defined in the standard, which is called vector. And it's defined to contain elements like magnitude and angle, which are both of the type analog value, which is again a constructed attribute class. And that's again defined in a standard to be on one side having an integer element or a floating element. And that's where we have now really the base type. So that's where we get to the leaf of our data model where we place the information in. Okay, Then Jackson also mentioned and showed that we have logical devices that group logical nodes. Logical devices are not standardized, but how we have to group the logical nodes, it's typically something that is defined in the device or can be defined by the user as well in devices offering more flexibility. Typical usage of the logical devices is to group logical nodes for protection functions, for control functions, as we have seen them in our example. Logical devices are on one side relevant for the naming hierarchy, but they are also relevant for the management of the device behavior. As an example, we can put certain logical devices in test mode in order when we do live testing. We will discuss about that in one of our future webinars. The information related to the logical device is in a specific logical node, and we call that logical node LLN0. So that's really the logical node that is specific to the logical device. We also have physical devices, as we mentioned, which is basically the same like an ID or an intelligent electronic device. Again, the standard does not standardize IDs, like what functionality should be grouped together in a device. This is an issue for the device manufacturer to build the devices as he thinks is useful and group the functionalities in. The ID itself has the infrastructure, of course, like the microprocessor, the power supply, but it also has the communication interfaces and the interface to the process where we can connect our system to the switchgear, to the breakers, but also to the current and voltage transformers. As such, we may also have information for our SCADA system related to the ID, like when we have a problem with a power supply or whatever. And for that, we have a non-logical node that we call the LPHD. So this is really the information now related to the ID. If you look at that, so we have our physical device. In the physical device, we have our logical devices. We have, in this case, 2 logical devices. In that, we have our logical nodes. And then, besides our specific logical nodes that make up the functionality, we have, as we just discussed, we will have in each logical device a logical node LN0, which has the logical device specific information. And in at least one of the logical devices, we have the logical node LPHD, which has the ID specific information. It may be, we may find this LPHD in all the logical devices, but the standard requires it to be present at least in one of the logical devices. After this overview on the elements, we will now start digging a little bit deeper into the IEC 61850 data model. On this first slide, I show the information that we have in the logical nodes, which is not really specific to semantic function. As I mentioned earlier, we have in each of the logical nodes certain information which is more generic, like nameplate information, health information, the mode. We will discuss some of those in future webinars and how we have to use them. In a similar way to this common logical node class, also our common data classes have certain attributes that will repeat across all the common data classes. They are the typical ones that repeat everywhere are listed here. One of them is the quality, which is the metadata for the data object, how the quality of the value is. Another one is the timestamp, and then we also typically have description attributes where we can put the description in what that data object means, and we can have that in visible and Unicode string. Talking about the data quality, in some cases you may not get the value correct from your source. Like as an example, when you have a value like a position of a breaker that is derived from a contact input into the device, and we have a problem with that contact, we will not be able to acquire the information. The data may still be communicated, but then we can indicate with our validity that the data is not valid, so that the data is invalid or questionable. It could also be that an analog value is out of the expected range, so something is suspicious there, then we can flag that as questionable. Usually the value should be good. That means we have the good value that we can use in our system for the other functions. If the value is not good, we can provide more detail why it's not good in our detail quality. 61850 also has a concept of substitution. So if a process value cannot be acquired, we can substitute it. An operator may substitute it because he knows, as an example, the earthing switch is open, then he can substitute it, and that's what we would indicate in this element, is this part of the quality that indicates the source. So by default, the source will be processed. That means it has been determined by our system. If for whatever reason we have to do a substitution, that will be indicated as substituted. Data attributes, the elements test and operator blocked. Test is mainly used in the context of testing a device in a live system, and this will be addressed in a future webinar. When we talk about analog values, as we have already mentioned before, the analog value can either be represented as an integer or we can have them as a floating point. If you use floating point values, the value that we put in is the primary process value. So we are not using secondary values, we are using primary values. So if we use the floating point, we will have the value in the attribute f, which will be a floating point value. If we use integer values, the integer value will be a scaled value. And in order to be able to determine what would be the process value, we also have configuration attributes. We have configuration attributes like scale factor and offset. So basically, we can calculate the process value from the scale value using these configuration attributes. Then a SCADA system can determine what will be the process value behind. We also can indicate the unit of the value that we transmit. So if we measure voltage, the unit will be volt, but we then can also use a multiplier. So we have the option to either, as an example, transmit the value in kilovolts. So in that case, our multiplier would be 3. And if we have 220 kilovolts, the value would be 220 that we transmit. But we can also decide to transmit volts, and then the multiplier would be 1, and the value in the F will be 220,000. The second aspect of analog values is how to communicate analog information when we do it event-driven. We know that concept already from SCADA systems, what we call deadbanding. So 61850 also supports the same mechanism. So basically, we have our analog value, and instead of each time we have a little change here to send an event-driven message to the receiver, we do a deadbanding. So at a certain moment, we transmit the value, and then we wait again until a certain deadband is reached. That can be calculated as an integral deadband, as an absolute one, and then we have a new value that we communicate. So instead of communicating all the time, we just communicate after the deadband. And IEC 61850 has the concept for that in the model. In our model for measured values, we have both attribute instantaneous magnitude as well as an attribute magnitude. The instantaneous magnitude is the one that is permanently changing. The magnitude is the deadbanded value. So that's the one that will be trigger an event-based communication like a report. Of course, if you do cyclic transmission for analog values, you can use the instantaneous magnitude. We also have the configuration attribute related to that. So we have a configuration attribute for the deadband calculation. And what you see here, we also have something like called a zero deadband. And that is basically used for another concept we know from SCADA systems, which is when the value is somewhere close to 0, which would be the case when a breaker is open, no current is flowing. From your analog digital conversion, you would typically have noise coming out, and to prevent this noise being transmitted, you can define a certain range where you will force the value to be 0. And again, we use the concept of magnitude and instantaneous magnitudes to model that. So our magnitude will be forced to 0 when we get into this range, and that's typically the value that you would like to see in your SCADA system. So with that, we have now another example of a common data class, our common data class MV for measured values, where we have the different attributes in this case of functions constraint mx that we just introduced. We also can have a range indication. We can configure ranges where the value is. We have our quality and our timestamp. And we have the related configuration attributes, deadband, zero deadband, the scaling of the value, range configuration, and the description. And we also have attributes for substitution. So this is just an extract. There's a couple of more attributes, but that's the most important ones. When we talk about the three-phase power system, we are typically not using the common data class MV for the three-phase values. For that, we have what we call a common data class Y, in which we have elements for the different phase values, phase A, B, C, but we can also have neutral, net, and residual values transmitted. Those are all of a type complex measured values. So here we can have both a phase as a magnitude as well as an angle. So that's of the vector that we have seen before. And then, of course, when we have vectors there, we need to have a reference for the vector for the angle. And that's one of the configuration attributes here that gives us the information what element of the three-phase power system is the reference from which we derive the angle. Okay, now that we have seen some of the common data classes, let's have a look on some of the logical nodes that we are using in our system. First, we will discuss how we acquire current and voltages. So basically, we already have seen we have the logical node TCTR, which is the interface to a current transformer. This logical node is single-phased, so that means we have one instance per phase. So we have B and C, so that's basically when we measure the currents of the three phases, we have these three logical nodes there. The same for measuring the voltage. The logical node there is called TVTR for voltage transformer. Again, we need one per phase. If you have a 61850 process bus system, so if the information is acquired in what we call a merging unit and communicated over the network to the rest of the system, that's when you use sampled values. So that's then this information is transmitted with sampled values to the devices that perform algorithms on them. As an example, we can calculate our RMS values in the logical node MMXU. We can also calculate harmonics, sequence information. But also protection functions are using these sampled values to perform the functionality. So any kind of the protection element or also protection related logical nodes can use this information. If it's a conventional approach, that information is in the same device, then this is more or less an internal way how the samples get into the function. But when you have a process bus, that's when the sampled values become relevant. Out of here, we have calculated values that we typically can transmit to our SCADA system. Now let's have a look at the details of some of these logical nodes. The first one, the logical node TCTR for the current transformer. The key data object here is the AMP-SV, what we call AMP-SV. That's a sampled current. So this is of a common data class for samples that are transmitted with sampled values. We also have a few settings related to the current transformer, like the rated current, the rated frequency, or the winding ratio. These are settings. They are used to common data class ASCG. As an example of one of the logical nodes that perform the calculations, we have the MMXU, the measurement unit, where we have data objects like current, phase voltage. They are of the common data class Y. So beyond here, we will find the measurement for the three phases. Current or voltage, we also have delta. That's what we use for phase-to-phase voltages. We can calculate power, active, reactive, or apparent per phase, but we can also calculate total active power. In that case, we are using a measured value. We can also calculate the frequency. It's just a few examples of the information we will find in a measurement unit. After having discussed a little bit about measurements, let's now get to control. We already have seen at the beginning of my presentation this common data class for controllable objects. I will not repeat the details here. We have the different configuration attributes. We have the status attributes related to it. From a logical node perspective, when we control a device, we have somewhere our HMI. The HMI typically sends a control request to the logic node CSWI. So the logic node CSWI is the functionality to perform a control operation. So that's where we also do the verification if the control operation is allowed. As an example, we will check interlocking condition. We have a logical node silo that is doing the interlocking evaluation based on different position. He may tell the switch if he is allowed to open or to close or not. If everything is okay, we may also need to check synchronism condition if we are closing a breaker on a lifeline. So we also have a logical node that is performing the synchro check analysis based on voltage measurements on the two sides, which is giving a release signal to the switch controller. And if everything is okay, the switch controller will issue the request down to the breaker to open the breaker. We get responses back that will also go to the HMI if the operation was successful or not. We also have protection logical nodes involved. So the protection logical nodes are permanently monitoring currents and voltages depending on the functionality. If a protection function detects a problem and has to trip, that will go directly down to the circuit breaker. It will initiate a reclose eventually if we have reclose functionality. The reclose may go down directly to the circuit breaker. It could also go through the switch, depending if we have to do again the checks with the reclose. So if it's a slow reclose, we probably need to do again synchro check. If it's a fast reclose, we can go directly to the circuit breaker. That depends on the design of the system. And all these logical nodes provide information to the HMI, like phase angle differences and so on. Okay, now looking at some of the logical nodes, here we have the logical node circuit breaker. It's similar to the switch logical node that we have seen, but so we also have one data object for the position, which is a controllable object. So it's a double point control. But now we have also some additional switch specific information, breaker specific information. One of them is typically the operating capability. Circuit breaker, as you know, has mechanical energy stored, and depending on that, he can make open and close cycles. So he can do a reclose, but at a certain moment, we need to recharge the mechanical energy, and basically on this data object, we can indicate the actual capability he still can do, which is important information for a reclosing function to know, can I still do a reclose or not? Because what you don't want to do, you do a reclose and then the energy is empty and you reclose on a fault and you cannot open the breaker. So that's one of the typical examples of information in. We also have information like point on wave. When you do point on wave switching, that means we try to close the breaker near the zero crossing. That's also some information we can find here. Some logical nodes more from the application side. Interlocking logical node basically has two key data objects. One that tells us if you're allowed to open the switch, the associated switch, or if you're allowed to close. So those need to be true in order to do an open operation. If this is false, the switch controller should not operate and will send a negative confirmation back to the HMI. I mentioned a little bit protection information. So protection devices, they typically have information per phase if the element operated or started, but we also can have a general indication, or we have the phase specific where we can indicate it was the phase A that has operated or started. In some cases, we also provide directional information, and that's what we find in our common data class ACD. So it has the same booleans for each of these phases and the general, but then for each of that, it also has a direction information, which for the general can be, I saw a fault in the forward or in the backwards direction, or for the general in both. For the phase specific, it can only be forward or backward. Another element when we talk about protection is what we call the logical node trip conditioning, or PTRC. So typically a protection device has these different elements that will determine if the element started or operated, and then we have the trip logic in the relay, which is modeled through the PTRC, and that's where we get a trip output that goes down to the circuit breaker in order to operate. And as I mentioned, all these protection elements typically have a start data object. That means a fault was detected or an unacceptable condition was detected, and it has an operate data object. That's typically when the function, the element operates. So we may have a timer between those. In some cases, start and operate may come together. In some cases, the operate is delayed, like in a second zone of a distance protection, you would have typically a delay between the start and the operate. And to summarize again, the hierarchy of our data model. So we have learned, we have an ID, the devices. In the devices, we have multiple logic devices. In the logic devices, we have logical nodes. They have data objects, and under the data object, we have our data attributes with the values. And with that, I hand over to Jackson that will explain you some of these elements now again on our practical example.
Excellent, thank you, Christoph. All right, so where we left off here in Test Suite Pro, just a couple moments ago, we were looking at the data models for these different devices. So let's start here again with the SCU, or switchgear control unit. So as Christoph told us, these different logical nodes contained within this logical device are going to have standardized elements. There are mandatory and optional elements, but there will be some combination of those, obviously all mandatory and some collection of the optional. So if we focus again on our XCVR, so this is an interface to a circuit breaker named QA1, I want to particularly draw our attention to the pause or position logical node. I always like to start with XCVR because I think it's maybe one of the more relatable logical nodes. This is telling us if a breaker is open or closed. Specifically, this position data object is, and then within it, we have our data attribute, STVal. So just like logical nodes have collections of mandatory and optional data objects themselves have collections of mandatory or optional data attributes, and that's what we see in here. Now, a combination of selected mandatory and optional elements make up a CDC or custom data class, as Christoph just described, common data class. So in particular, let's look at this STVal, and we see that the current value is on. So again, focusing on the semantic portion of the data model, I now know that in the D1 voltage level, in line 1, there is a circuit breaker named QA1. I know that its position, status value, the actual value of the breaker, is on. Of course, as Christoph said, there's other data attributes that we'll see in here: quality, timestamp, prop OK, a description value, things like that. So let's take a peek at a couple other logical nodes. First, I'm going to switch up to the BCU, or Bay Control Unit. So we talked a little bit about measurement before, and we talked about the MMXU. So here we'll see the different data objects contained within it. So for example, MMXU is going to have all my measurement values. If I wanted to see current for a specific phase, then I could expand that out and look at, for example, the A phase current. As we said before, data objects can themselves contain data attributes that contain, even below them, sub-data attributes. And we see that as an example here with the instantaneous and current value for MMXU currents. Now, as we spoke about before, there was actually two logical devices on this BCU, the other one being the control logical device. And as I stated in the first demo, this is where commands will come down from SCADA in order to operate a particular breaker. So QA1, that might sound familiar. We just talked about breaker QA1 when we were looking at the switchgear control unit. But now this is the CSWI, the switch controller for that breaker. So if I wanted to operate the position value as an example for this about that, guys. I dropped off for a second. And I'm going to try and pick back up where I left off. So over here on the left-hand side, we see the different data objects and data attributes. So for example, CSWI, sorry about that quick drop off. And then the position data object. So if I want to actually operate this one, I'm just going to go ahead and right click and select and operate this node. When I do that, I can change the value. In this case, I'm changing from off back to on. Just go ahead and hit OK. And it actually issues that control back down from the CSWI logical node, ultimately down to our breaker operating that value, which is then reflected back here. This status value that we see here, indicating that breaker's on, is ultimately coming from that XCBR. So finally, I want to switch back over to our LPU, or I'm sorry, I want to go a little off my game here. Yeah, let's see, go back over to the LPU, or line protection unit. Again, we had two different logical devices on this device, the first of which is going to be the control logical device. In that, we can see the different data objects or logical nodes that are controlling this particular bay. So one example of those would be the RREC, or recloser, that Christoph talked about. And inside of that, we'll see different data objects that are going to relate to different parameters that we want to model for this recloser. So as an example, we have the auto recloser state, and I'll walk through what that means in just a moment. And then we'll see several different timer values here, indicating how long we should stay in those different states. So basically what's happening here, a fault occurs, the breaker opens, try and clear that fault on the line after a short period of time defined by the recloser 3 TMMS. We'll actually try and reclose that breaker, and then wait for the reclaim time, and then ultimately ready TMMS time. And I can expand these out and see what these values actually are by issuing a read. So 500 milliseconds in this particular case. So to kind of see that in action, I've set up a logic analyzer diagram, which is what you see here. So here I've issued or simulated a fault on my line, which caused my PTRC to try and actually trip my breaker. Short time later, the breaker actually opened, and the fault was cleared, and it successfully reclosed. So to look at that from the perspective of the recloser logical node, we could step through these different states as this line steps up and down. So first, initially, before there was any fault, we were in this ready state right here on the left-hand side. Once the fault was detected, we did move up into the trip from protection state. So the PTRC right here actually issued that trip. Again, moving forward, a short time later, the breaker actually opened and the fault disappeared. And then from there, moved into in progress. So that was just basically a waiting period to see that the fault would continue to remain closed. I'm sorry, continue to be disappeared while the recloser does its job and issues the reclose attempt. A short time later, the breaker does actually close, and then finally we move into a successful state. And once that final timer expires, we're now then ready. We can return back to a normal state. So again, these values here are all coming back in through the auto recloser's SD status value, which was just this value right here. So, ready is an example, but all those other values that we saw before are going to ultimately be coming in here as well. So with that, I hope I've been able to kind of illustrate how some of these abstract topics that we've been talking about actually relate to an actual substation and the devices and functionality within it. And I'll go ahead and turn it back over to Christoph for a final few slides before we end with one last demo.
Okay, thanks, Jackson, for this good introduction, for this excellent demonstration. So, just getting back. Okay. What we now continue, so now that we have seen a little bit the details, how they work, we will explain to you a little bit where in the standard you find these different elements defined that we just learned. So basically, it's the part 7.4, and we have also some other parts like 7.410 that are more related to distributed energy resources and hydropower. 410 is hydropower, distributed energy resources 420. So in those parts, we basically define all the logical node classes. We define the semantic of the logical node, the class name, the structure, what data objects are included, and what is the semantic of the data objects. The data objects are referring to the type, which is the common data class. The common data class is defined in part 7.3. So part 7.3 defines all the common data classes and constructed attribute classes that we can use in the standard. And then we have 7.2, that's where we find the basic types and common ACSI types. 7.2 is more related to communication, but as the basic types and common ACSI types are also used in the communication, that's why those are defined in 7.2. Now, how is this done? We have an example here for the logical node XCBR for the circuit breaker. So this is a text extract from the standard, how the logical node is described, where we basically say how it has to be used, what it is intended for, how it relates to other logical nodes. To define the content of the logical node, we are using tables. Tables, like we have an example here again, it's an extract from the complete definition. We have a list of our data objects. They are grouped depending on their characteristics, like we group all the controllable objects or the status information. We have a reference to the common data class that we are using. If it's enumerated values, enumerated common data class, we also give a link to the type that defines the enumeration. We have the explanation of the data object, and we have an indication if the object is mandatory, if it's optional, or if it's there under certain conditions. For the data object, then we have a detailed definition of the semantic. Again, if it's an enumeration, we provide the enumeration information. So like this is the operating capability of the breaker. If the value is 1, that means it cannot operate anymore. The mechanical energy is empty, and so we have the different values here. Common data class is the same. They are defined as a table with the attribute type, which can be a basic type or it can be a constructed attribute type. We have the function constraint information. We have what we call trigger option that we will discuss more when we discuss the communication of 61850, like the reporting. We describe what it is used, and we indicate again the presence condition, if it's mandatory, if there is a certain condition when it has to be, or if it's optional. Again, the detailed definition of the semantics in a textual form, like here for the timestamp, also to what it applies is described here. And constructed attribute classes, finally, that are also defined in 7.3, again, are defined as a table with explanation what the different elements mean. We talked about function constraint. This is the list of all the function constraints used in the part 7.3. The first one's highlighted in red. That's really where we find the operational information, the live information from our system. This is more the metadata attributes like description or configuration information. And the last two slides here, just an overview on the basic data types and common ACSI types that are used across the system. You will get these overviews. I mean, you will get the slides at the end. So you have this collection there. And this slide summarizes again where we find what in our data model. So in part 7, in our standard, in part 7.4, we find the logical nodes. We define the data objects that are member of the logical nodes. They refer to a common data class, which is defined in the part 7.3. Common data class defines the different data attributes. Data attributes can be of a basic type, they can be of a common ACSI type, but they can also be of a constructed attribute class, which is also defined in part 7.3, with subdata attributes, which can be of a basic type or which can be on another constructed attribute class. And then in part 7.2, we have the basic types defined and the common ACSI types. Before we get into the last part where we discuss about the system configuration language, I hand over to Bess for some questions.
Okay, great. Yeah, we do have a couple of minutes. We're doing good on time, so I'm going to pause for about 2 or 3 questions. The first one, I believe, is for Christoph. What do the substitute values do when they are enabled?
Okay, we didn't discuss the substitution in details in this webinar, but basically the way how substitution works in IEC 61850 is that you have attributes where an operator can write the value he wants to substitute. So as an example, if we lose the position information from a switch, we can write the value there that we know if we know that the switch is closed, we can write that value there. And then there is another attribute that we use to enable the substitution. And once we enable the substitution, so we write the true into that attribute after we have written the value in that we want to have. Once the enable is active, what we will see communicated from that data object as status value will be the substituted information, and at the same time in the validity we will indicate now that data is not from the source anymore, but it's now from the substitution. The source is not anymore from the process, but it's now from the substitution.
Okay. Next question, I believe, is also for you, Christoph. LNCSWI handles control. Could it also be used to forward circuit breaker position indication instead of using XCBR?
Yes, that can be used as well. So typically the circuit breaker position will get into the CSWI, and the CSWI has also position status attribute, so we can also use that. There may be subtle differences in the timestamps, and definitely when we have single phase systems, then we have individual XCBRs per phase. That's when we typically take the information from the XCBR. But yes, in principle, we also find that information in the CSWI.
Okay, thanks. Next question, I'm going to throw this one over to you, Jackson. Is the model browser only available in the new version of Test Suite Pro?
No, it is not. It is also available in version 4.7. We kind of changed the name. It's known as Advanced Client in Test Suite Pro and Test Suite Lite. But no, it is most certainly available. You can browse data models for individual devices, issue controls, subscribe to reports, subscribe to Goose messages for that matter. All of that functionality is absolutely available in the currently released version of Test Suite Pro.
Which can be downloaded from the website today as an eval.
Yep.
Great. Okay, with that, Christoph, I'll go ahead and hand it back to you.
Okay, so to close out that webinar, we will now discuss a little bit about the system configuration language of 61850 with a focus on what we just discussed on the data model. So what we have discussed so far was basically what is defined in the part 7 that defines the structure, how we can transmit values from the system over the communication, how we can model them. But we also have in 61850 elements to describe how we configure the system. So how many logical devices, how many logical nodes does an IED have? So we can also represent that in the 61850, and that's what we call the instant configuration model, and that's what we also call the system configuration language, and that's defined in the part 6. So the part 6 basically describes a language how we can create files that describe the configuration of our system or of our device. It's based on XML, standard from the web industry. It also defines processes how to use these files for the engineering of a system. It defines tools, tool roles, and requirements to support this usage. In the part 1, Jackson has introduced this high-level view how we use the system configuration language with the different files from specification, describing an IED, the system tool that builds the system and creates the complete file with all the configuration that is then used by the IED tools to download in the devices. We will not focus much on this engineering process today. For that, we have an own dedicated webinar in the future, but we want to introduce basically how an IED is represented in that SCL model. The complete model behind this system configuration language has multiple levels. We have one level where we describe the system itself, which means the substation with the different voltage levels, the bay, conducting equipment like breakers or measurement transformers, power transformers. And we also can describe the topology, how this conducting equipment is connected to each other through the connectivity node. We'll discuss about that in more details in one of the future webinars. The second part of the model that we have in SCL is the ID data model. So here we can describe the structure of an ID, what are how the server in, what are the logic devices, what are the logical nodes, and what are the data. That's what we will focus on a little bit today. And then we also have a part that is describing the communication network. So we have can have multiple set networks. We have access points, and associated to the access points, we have our servers in the IDs. So this slide here gives us the full simplified model described in SCL. And as I said, we will focus basically on this part today. How do we describe the data model and the capabilities of an ID in SCL? So the SCL file has basically multiple parts. It has a substation part where we describe the topology. For each of the ID, it has an ID part, it has a communication part, and we also have data type templates. So basically, what we will have a closer look now is how this ID part is presented. So this is the first example. An ID has a server which is associated to an access point. We may have multiple access points that use the same server, the same model behind. So in our SCL file, we have the ID element. Beyond that, we have access point, we have the server, and then we have our data model, logic device, logical nodes. In the service section, we basically describe what are the capabilities of the ID with regard to communication and engineering flexibility. And this part is really describing the data model. So if you look at an ID and the properties of the ID, what do we really need to describe for the ID in our SCL? So an ID has on one side aspects of the data model. So the ID, depending on the functionality it supports, has logical nodes, has data attributes, as we have learned in the standard. Some of the data attributes, data objects are optional. We also have to describe which of the ones are present. So we cannot just refer to the standard. We have to list the data objects that are really present in our model, because from a standard perspective, not necessarily all need to be there. Regarding to the data model, we have also learned that we have, in some cases, settings, so parameters where we can configure values. We also have configuration attributes where we can configure values. The second aspect of the characteristics of an ID is related to the communication. So we can describe what are the communication services supported by the ID. Not necessarily every service is mandatory from the standard, so we can describe what is supported by the ID. Also, how flexible is it from an engineering perspective? And then, of course, we also have to describe the communication behavior, what has been configured as goose messages, as sampled value messages, or as reports. This will be discussed more in the future webinar when we talk about configuration, but here we will have a focus on how the data model related aspects are defined. For these properties, basically the left part, that's what is describing how the ID is designed. So that's typically not changed during the system design, because that's characteristics of the ID. The right part, that's typically what we change when we engineer the system. So that's where we can do configurations when we build the system. Okay, now how is that translated into XML or into the SCL, the system configuration language? As we already have seen, we have on one side the data model. We list the logic device, we list all the logical nodes, and instead of referring to the details of the logical nodes here, we refer to what we call a logical node type. And that's where the data type template section comes into the game. So we have logical node types that we can reuse in multiple of the logical nodes, where we define for this realization, we just use the data object AMP out of the data objects that exist in the model of the standard. The type again, which is the common data class, can again be defined through a template. Also the attribute types, if this is a structure, can be again defined through the template. And Jackson will show that in the last demo just in a minute. So that's how the data type template section works. And then we also can pre-configure values. We have seen we have configuration attributes, we have parameter settings. So we can also pre-configure those values either in the template or in an instance. We have here a first example where we have a data type template for the nameplate. We can configure values like the vendor, software revision, namespace, and other elements. If we do that on the template level, all logical node instances that use this template will have the same values. In some cases, we will have individual values per instance of a logical node, like here, which is shown on the right side. So here we can define on this logical node pthis, that for this first instance, our operate delay time setting is 0. So that will be the zone 1, where the operate and the start are coming together. The zone 2 element, which is typically delayed, we can here configure the operate delay setting, in this case, to 100 milliseconds. So that's where we can configure individual values in our SCL file. And Jackson will now show that on a practical example again. So with that, I hand back to Jackson.
Thank you, Christoph.
You should now be presented.
All right. So what you see up on my screen now is SCL Navigator. So SCL Navigator is so let's call it a 61850 aware editor. It allows you to create SCL files, typically ICD files, and other files that are used earlier on in the engineering process. But you certainly can open, edit, tweak, and make changes to any SCL file from any point in the process. A lot of times when we bring it up, we're talking about its validation capabilities. So you can run a set of OCL rules that will validate your files to make sure that they are correct. But today I'll just be using it to open up the SCD file that we've been talking about all day, or that I've been using in my last 2 demos. So this is an SCD file, or system configuration description file, for a substation. And of course, we see the different IEDs represented by these different rows over here. So just to refresh on some of the different parts of an SCL file, as Christoph talked about, up here at the top, we just have the header. So it contains edit information, changes that were made over time to the file and why, and what revision or version it is. Moving down into the substation section, this is commonly created as part of the specification stage, and you can actually put topology information about your substation, what breakers and switches are present, who's connected to what in a physical system. The communication section down below, this is where we're going to have all of our IP addresses, VLAN IDs, any communication settings. But really where I want to focus today is this IED section down here. So we'll pick one of those IEDs. Let's go with the D1 line 1 SCU that we spoke about before. So as part of the engineering process, and we'll talk about this in a future webinar, but you're taking these different ICD files that are provided by vendors, and you're kind of merging them together and doing your system engineering. That's where this model originally came from. So as I expand it out, I see the services section, just describing some of the capabilities of this particular device, and then an access point. This effectively refers to a physical net or network interface card on that device. And then down within that, we have a server. And then this is where we begin to see the actual data model that we've been discussing, right? So we see the logical device, the same one that we saw over in Test Suite Pro moments ago, control. And within that, we see a group of logical nodes. So I'll go ahead and collapse all my logical nodes so I can see them in a nice list form. Importantly, down here, we see the XCBR. So this is the one that I kind of kept coming back to throughout this webinar. So I'll come back to it one more time. You might remember in Test Suite Pro, we saw the name of this XCBR. It was a concatenation of these several variables. So QA1, our prefix here, refers to the specific breaker that we're interfacing with. The LN class, XCBR, this is the logical node type or class. And then finally, the instance number over here on the right-hand side. Now, I might have multiple XCBRs throughout my substation, and they may or may not have the same collection of data objects. As Christoph talked about before, there's some that are optional, some that are mandatory, and that collection of optional and mandatory is in this case defined by the LN type. So because it might be reused throughout the substation, you'll see that you don't actually get to see the data objects here in the IED section. That's where the data template section comes in. So as I said before, there's a couple different sections to the SCL file, the bottom one being the data template section down here. So let's expand back out this device, find that XCBR again, and then I'm going to right click and navigate to the template. So again, if this CBR, which in this case it actually does, the same template or LN type is used on multiple IEDs, each one of the bays in this substation. So I just need to define it, or it just is defined a single time in the SCL file. And that's what we see right down here. Of course, contained within logical nodes are data objects, and that's what each one of these rows are right here. So we've been talking about the position or pause data object. If I want to see what data attributes are contained within it, then I could just right click here and navigate to its template. So we're now kind of at the bottom of the tree. This is a specific data object CDC or common data class and the list of data attributes that are within it. So the one we've spoken about before is actually going to be the pause.stval, and that's going to be this guy right here. So just to kind of reinforce another one of the concepts that we spoke about before, so that's the templating, the ability to have, an LN type with a collection of data objects, and then data object with a collection of data attributes. I'm going to show what that looks like. To do that, I'll navigate back up the tree to my XCBR that uses this data object or CDC, and then I'll navigate back from this data object back to my line 1 SCU. Okay, so now when I select this guy in the tree over here, it's going to navigate, or it's going to highlight and navigate to the appropriate data object and logical node, I should say, in my tree over here on the left-hand side. If I wanted to make an edit to this template, it's just a right click and edit. What that will bring up is the template editor for this particular logical node. So you'll notice this column right here indicates which data objects are mandatory and which ones are required. So you notice there's really not that many that are mandatory in this case, only a handful. And we have them, of course, turned on. That's part of what mandatory means. And I could find my position data object again. And then if I was to click over here on the CDC name, then I could create a new one. So in this case, let's say I want to add a block enable value. I could add that in. Of course, this is going to be an optional one. My ones that are grayed out and checked are going to be the mandatory data attributes in this common data class. And then I'll just give it a name. Now, if I was to, again, navigate back down, we can actually see how that affects the file. So I've come back down again to my LN type describing this XCBR logical node. And then we'll notice the type now has changed for position. It's now called my CDC, my common data class, which I just created. And if I navigate to that template, you can expand it out and see the different data attributes contained within it, including that block enable that I just added in order to model my breaker maybe more accurately or more fully. So with that, I think we're coming to an end here of my demonstration. So I'm going to pass it back to Beth one last time, and she will lead us through a couple more questions and provide a little bit of wrap up. I do encourage you guys, if you have not already, please check out our website and look at that exercise that we did for webinar 1.
Okay, thanks, Jackson. Yeah, I think I'm going to just spend a minute wrapping up here, and then we have been getting a lot of good questions in throughout the webinar. So we do have some extra time, so I will go through some of those as we wrap up. So first, I just want to thank everyone for joining today and spending some time with us. So there's a couple of ways that you can get access to the recording of this training session. If you go to our homepage and you sign up for our newsletter, you'll get information on Triangle's product updates, training events, webinars, links to the recordings. So that's how you get all the updates from Triangle. You'll also be presented with a survey after the training session is over, which will ask you if you want to just join the mailing list specific to the 62150 training series. So if you just want to receive notifications on that, go ahead and click yes, and you'll be added to that list only. You can also request to get a copy of the slides. And again, just a link sent to you, but the link ultimately is posted on our website in the next couple of days. I will also point out just one last time in the handout section of the webinar toolbar, you have the links there or the documents for the previous, for part 1, companion layup exercise, the reference document, and I did put in the chat the link to where you can get the part 1 recording. And then of course, we'd love to get any comments or feedback from you. Please feel free to email sales@trianglemicroworks.com. We'd love to hear from you. So with that, like I said, we've got a lot of good questions in. Let me go ahead and start with some questions as we still got a couple minutes left on the clock. Christoph, I think this one's going to be for you. Can Goose be used vertically with SCADA for multiple clients instead of using reporting and creating multiple reports that have the same data set?
Okay, thanks, Beth, for the question. So the quick answer is yes. In principle, you can use Goose between whatever devices you have. So you can also use it to go from an ID and be subscribed by like a gateway or an HMI. But keep in mind that when you use Goose for that purpose, first of all, it's published and to everybody at the same time. And if your HMI is offline or you have lost the communication, you will not be able to later on get the events. That's why we have typically reporting with buffered reports, so you get the events will be buffered and you can get them later on as so you can establish your sequence of events. Also, in Goose message, we typically don't include a timestamp, just for also not to overload the communication. So if you would include all the timestamps in Goose messaging as well, so that you can subscribe to that and get your timestamp of the information, that will create much more overhead. So reporting, to be using reporting up to a client is definitely the more efficient way to use our communication.
Okay, next question. Is data attribute D from CDC SPS same as from CDC DPS? If not, then how do you decide which one to use from which CDC?
I'm not quite sure if I understand completely the question, but so basically, yes, in each of the CDCs, it's defined that we have a data attribute D, but of course, at the end, this is individual attribute. So you have a data object like the position, or from a CDC double point control, the position will have an attribute. This data object position will have an attribute D, where we can put the description of the position in. But then you may have an alarm, which is of a common data class SPS, that has also a description attribute, but that's a different instance now, because that is an attribute of this alarm object. So all of them get instantiated with each data object. So at the end, we have plenty of D attributes basically for each data object that exists. We have its own D attribute. Not sure if that answered the question, but I hope.
Mm-hmm. Okay, next question. I'm going to throw this one over to you, Jackson. In the SCL editor in the OCL validation tool, is there a way to update the OCL schema to be used?
Yes, so you certainly can update OCL rules as they are published by Working Group 10. So there's a way to basically import the OCL rules that are used by the OCL engine the OCL engine being rise clips that's actually running under the hood. So you're not reliant on the set of rules that were provided when Navigator shipped. If you want to write your own custom rules, you can certainly do that in OCL, which is object constraint language for those of you that aren't familiar. If you're specifically referring to the schema, there is a method to do that as well. You can basically navigate through the folder structure and find where we store the different schemas and replace those with custom sets as well.
And just a follow-up question to that, is the OCL schema changing often?
So I'm assuming that the question there is really referring to the OCL rules, because that's the more direct, I guess, set of things that's related to OCL. Yes, I would say it is. If we're referring to the set of rules that are used to validate SCL files, there's an active task force that's working on it, and they are coming up with new rules fairly frequently. Anyone can join Working Group 10. I suppose you got to be nominated by your national committee, but you can then join that task force if that's something that you're interested in. They are publishing those rules relatively soon as a code component available as part of the standard. So yes, I mean, there is active development going on in it. I wouldn't want to frame it like, oh, something's changing. Like that, it's not actually the schema that's changing. It's just a set of validation rules.
Okay, thanks, Jackson. Oh, go ahead.
Maybe I can add on that, as I'm involved in the working group. So basically, I mean, yes, currently we are building up all these OCL rules. Once we have them defined for each of the parts, the idea is whenever we have a new extension or a new element of the standard in the future, we'll also at the same time, like we develop the standard, we also develop the associated OCL rules.
Okay, great. Next question, I think this is going to be for you, Christoph. What is the purpose of the data type template section? Isn't this data already defined in the standard in the NSD files?
The standard and NSD files define the data structure that exists in the standard, yes, but as we have learned today, not all the data objects and not all the data attributes of a common data class are mandatory. So in the data type template section, we describe what is really supported by the device or required from when we do specifications. So we have a subset there from what is completely defined in the NSD files or in the standard. So that's one aspect. The other aspect is as well, and we don't have time to discuss that in detail, but the other aspect is as well, the 61850 standard allows to make extensions to the data model as a user, as a device manufacturer. If you have certain information in your algorithms that is not yet standardized, you can also extend the model, and that's again what you would describe in this section.
Okay, next question. What is the importance of service under IED?
That's probably also for me. The service section in the IED, as I shortly mentioned, but I didn't go into details, that's where the capabilities of the IEDs are described in terms of communication and engineering flexibility. Not necessarily all communication services are required. As an example, sampled values is typically only used by a merging unit that transmits sampled values. So in the service section, the IED indicates what services are supported. So that's one important part. But then it also indicates a lot with regard to the engineering flexibility. Depending on the device, and we will talk about that much more when we talk about the engineering in one of our future webinars. But that's basically where the device declares how many report control blocks can be configured by a configuration tool, how many data sets can it have, how long can a data set be. So all kind of constraints that we also find in the PICS list, the protocol implementation conformance statement, all these constraints are described there in a machine processable way so that the engineering tools know what they can do, what they're allowed to do, and what they are not allowed to do.
Okay, thanks, Christoph. Next question, I believe this is for you, Jackson. Is it possible to create my logical node or customize the existing ones in an SCL file?
Yes, absolutely. But I would say context also matters there. So if you're a device vendor, then that's a big part of your job when you're creating the ICD file for your device. So you know, as a vendor, know the capabilities of a particular device that you're building, and you reflect those capabilities or model them in an SCL file, typically in ICD. Now, you can certainly also do this in other contexts. If you know you're configuring a gateway, for example, and you need a data model for your server, that's another instance where you would create and modify the capabilities of a device. But if you just purchase a device off the shelf as a system integrator or utility or someone, and you can't necessarily just open up that file, add functionality there by editing the SCL file and save it and push it back down, if that particular device doesn't support it. Christoph, if you have anything that you'd like to add, go ahead.
I think answer was fine.
Okay. Next question for you, Jackson. Can Test Suite Pro also simulate the functionality of logical nodes, for example, using scripting?
So for that, we typically point people towards another one of our tools, DTM or Distributed Test Manager. So in Test Suite Pro, you do have the ability to simulate servers coming in version 5.0, which is the one that's coming out this summer. You can interface directly with the simulated server using I'm blanking on the name of the tool, the test sequencer, but it's still not really a scripting method. It's a procedural list of instructions that you can manipulate data on a simulated server. If you want to simulate functionality of a particular device, or take it all the way down to the logical node level, then that's absolutely something that we recommend you use DTM for. It's actually how the simulation is working that I was interacting with today. So when we saw that logic analyzer chart showing the different states of the recloser, that was a scripted functionality. We basically looked at the standard, saw the different states defined for the recloser, and implemented a state machine in scripting for the recloser logical node. So yes, absolutely you can do that, but I would recommend DTM or Distributed Test Manager, also available from the website for a free trial.
Great, thanks, Jackson. So we're a little bit over time. I'm going to end it there. Again, I want to thank everyone for your time and really appreciate if you could take 2 minutes and fill out the survey. We appreciate any feedback that you can give us. Okay, thanks everyone.